going out to this line. So you need to write the equation of the line, right? Not the equation of the circle. Here, R was reaching out to the semicircle or the circle. Okay. So what is the equation of this line? So nice that you put this point at 0, 0. This point is at 8, comma 10. That's going to get reduced, but y is equal, I don't know where I can write. Y is equal to up 10 over 4, so 5/4 x. And if y is equal to 5/4 x, x is equal to 4/5 y. What are our limits? If I'm filling it all the way, then 0 to 10. If I'm filling it halfway, 0 to 8 is where the sections would go. Teo, did you have a question?
Isn't the radius supposed to be squared?
Yes. There you go. 0 to 8, 0 to 10, if we are filling it all the way up. Any questions? Any swimmers in the house? Henry and swimmers. Who are my swimmers? Henry and Tomo? Yeah. And Matthew? We have a trapezoidal pool. Lacrosse is a field, a rectangle field. Ooh, so exciting. My pool, from a profile of it. Let's see. Sorry. Looks something like so. It's going to be not so scale model, right? Not actual size. There's a deep end that is pretty long, and then it gradually, or the shallow end right here, but I drew it in that direction on purpose. So this is the shallow end, right, and it progressively gets deeper, and then the deep end is deep for a while. This is probably more curved. It doesn't just go slanted like that. So it could maybe be parabolic, and so I would represent that with a equation of a parabola. I'm making it linear just to simplify things for us. Okay. So here I would be around this part, because I can't swim. I'm sharing all of my deficiencies with you today. Let's say that this pool is 7 feet deep. It is 9 feet wide along here. It is only 7 feet deep for about 3 feet. Or meters, or whatever makes sense to you. Again, I don't care. Make it accurate if you'd like. And it is about 5 feet wide here. Yes? Can you kind of imagine that? So you can't actually see it because usually a pool, you just see the rectangle on top of it, right? And then you can't really see all the way down and so on. But here's my pool. Where would you like the X and Y axes? Left, right here for the y-axis would make the most sense, right? And for our x-axis, maybe along here. Do you want to pump water into or drain the pool? Drain? Okay, let's drain. Let's drain the swamp. So draining it would be coming out of the top, right? Bailing water, right? A lot of work done. So it's going to be coming out of the top. Empty from the top. Because from the bottom, we would just have Henry swim all the way down there and open the drain, and then it's gone into the ground, right? Here we're bailing water out of the top, removing one layer at a time, and so on. Top layer is your biggest layer, it looks like, right? Bottom layer is your smallest layer. What are the shapes of these layers?
Rectangle.
They are rectangles. So when I do my force and I'm calculating the volume, now I'm using the volume of a rectangular piece, right? Not a circular piece. So if I were to draw one little sliver of it, I don't know if you can kind of tell, but it's supposed to be rectangular-ish, yeah? And what's the distance or the displacement that this piece moves? Coming out of the top. 7 minus y, right? Yes, but so that's where I'm measuring from the top to here, right? Because it's coming out of the top. Here, would that make it better? If I draw the arrows in both the directions. All right, so this distance is 7 minus y. What's my radius? There is no radius. This is a rectangular piece, right? So force is equal to, I'm just going to go ahead and put in that omega times density, right? Times the weight. The weight is going to be length times width times height, because there's a little volume, sorry. So this is omega, this is the width of that rectangle. What's the length of it? X. What's the width of it? 5. Oops. Times x times 5. What's the height of it? dy. What's the equation that relates x to y? Where's that equation coming from? The slopey line. Yes. It's going out to this line, so this line is what you are writing the equation for. Equation for the line, best formed from point slope form. What's this point? 3, 0. This point is 9, 7. Bless you. So which point do you want to use? 9, 7 or 3, 0? No, 1. Point slope. Point slope. 3, 0 is easier to use. Y minus 0 is equal to slope from here up. From here up, 7. From here across, 6, 7, 6. Right. X minus 3. Slope up 7, across 6. Don't use slope-intercept forms. Slope-intercept form is for babies. We good? So x is equal to y plus 3 times 6/7. No. 6/7 y plus 3. No parentheses. Yeah. X is equal to
6/7 y plus
6/7 y plus 3. It's right now. So, amount of work done in emptying the pool from 0 to 7 times omega, null pi, right? Times 5 times 6/7 y plus 3 dy. Don't forget that. So this is just the force, right? Times 7 minus y. Any questions on that? How many of you been scuba diving? So for someone who can't swim, me, not him. I can swim from one side of the pool to the other, so I can not drown, but put me in an open water, I'll die. I can't get from one side of the ocean to the other side. So you would think that scuba diving would be fun. It's not. It probably could be eventually, because all you do is really sink to the bottom, or you're supposed to, right? Sink to the bottom, and hopefully you're not too far out, so you're walking around on the bottom here for the most part, looking at the pretty fishes and so on. But you're also panicking about breathing into this apparatus that you're not, and you're supposed to just breathe regularly, but it's very it was very claustrophobic to me. It was like, you're not supposed to do that, right? But the lower you go in scuba diving or into the ocean, the more pressure acts on you. So that's why when you get out, you're supposed to go up gradually so that you don't blow up or whatever. Like if you zoomed out or something or dropped down, then the amount of pressure is too much, or the change in pressure is too much, and so on.
It'll cause the blood in your veins to carbonate.
Yeah, exactly what he said.
Mm-hmm.
Okay, so if you are up here, not feeling as much pressure, and if you can tread water, you're like even better, and so on. I'm just going to be flapping around, but less pressure here, less force here than there is here. Okay. Similarly, if I had a container with water and I submerged something horizontally, not my phone, but you get the idea. If I submerged it horizontally underwater, then there is the same amount of pressure all along because it is at the same depth. Okay? So if my rectangular container is submerged horizontally, then the depth is all the same everywhere along it. Okay? Whereas if I submerge my phone this way, there is more pressure down here than there is up here. Probably not a whole lot more, but there is more physically. Okay, so things down here feels more pressure than things up here do. So if I were to submerge a sheet, rectangular sheet, oval sheet, circular sheet, it doesn't really matter. What matters is that there are different layers, right, that feels different amounts of pressure. So this is a different amount of pressure than these do. Even if I had submerged it about the same level as this one, only one level would feel the same amount as the horizontal one, right? Everything else feels either less or more depending on the depth of it. This physical application is what we call fluid force. And the fluid force depends on the depth and the area that is exposed in a horizontal direction. So fluid force, F, is equal to area times depth times the density. So again, if we were to submerge an object in water, there is pressure acting on the side of it, more pressure up here than there is down here. But if I were to submerge this into molasses, there's even more force that is acting on it, okay? Because of how dense the object is. But density for us is just omega. The depth is something that will vary, right? That's the whole point of it, is the different depths gives different amounts of pressure and therefore force. And the area only amounts to this length, L, times the little thickness of it, that sliver. So you're thinking of like a sheet of paper. What is the area of that sheet of paper? It's L times dy. So L times dy is your area. So just like what we did with our work, all of this is going to be calculated or set up in the dy direction. F, the amount of fluid force or force acting on a vertically submerged object, is equal to the integral from A to B of omega times L times d dy, where d is the depth and L is the length, if you will, at that of the object. So in our pool, the water that was in the pool, because we emptied it now, but there used to be water in there. This is going to be not drawn to scale. It's pushing at the side of the pool, right? So that if there was a crack, it would come through the water, right? It's pushing against it. So this is a profile of the pool. We said this distance here was 3. This length here was 7. This length up here was 9. The 5 is not going to come into play because everything along that 5 is the same as whatever the depth is. I'm going to have my pool filled up to 6. So the entire length of the pool, or height of the pool, is 7, but the water is only going to go up to 6. What is the amount of force that is acting on the pool, or this side of the pool? So here's one layer. Here's another layer. Here's another layer. Depth is always measured from the surface of the water to the layer. So what's depth in this case? 6 minus y. What's the length? This length is x, where x is coming from the equation x equals 6/7, right? Or we had originally written y equals 7/6 times x minus 3. And therefore x was equal to 6/7 y plus 3. Force is equal to the integral from 0 to 6. The only amount of pressure comes from where the water is, and the water only goes up to 6. Length? 6/7 y plus 3 times depth, 6 minus y dy.
And omega.
Omega, yes, thank you. Yeah? How many of you been on a cruise? A cruise. How many of you been in submarine?
One of those